Hello students, let's discuss few numericals from lesson dual nature of radiation and matter. Before starting with this lesson, numericals, we'll be discussing formulas which we are going to need. So you can see here first formula E is equal to h nu, where E indicate energy, h is Planck constant and this symbol is nu, and this nu is nothing but frequency. Instead of frequency, we can write same formula in terms of wavelength, which is so we can write instead of frequency C upon lambda. So for energy, formula is equal to h nu, which is equal to hc upon lambda. Then for momentum, formula is E upon C. So we can put instead of E, h nu. So formula for momentum we can write in terms of h nu upon C, which is equal to h upon lambda. So depend on wavelength is given or frequency is given. Accordingly, we can use this formulas. Then this is symbol for phi. This phi is nothing but work function. And formula for work function is phi is equal to h nu naught, where nu naught is threshold frequency. Then third is half mv square max is equal to v naught e. So half mv square max is nothing but kinetic energy, maximum kinetic energy. V naught is indicating threshold stopping potential, and E is charge. Then formula for kinetic energy max, which is equal to half mv square, is equal to h nu minus phi. And instead of phi, we can put h nu naught. So after putting h nu naught, formula which we will be getting, that is h nu minus nu naught. And again, if in numerical it is given wavelength, then instead of frequency, we can write C upon lambda. So this formula we can use h into C upon lambda minus C upon lambda naught. And we can take it out C common. So hc into 1 upon lambda minus 1 upon lambda naught. And if in numerical, we need to find out maximum velocity, then we'll have to just rearrange this fourth formula. Then we can get formula for V max or V square. So formula for V square will be formula for V max will be V max is equal to under root twice h nu minus nu naught upon mv. So these are required formulas which we are going to need. So you can see question number 7 here. So what will be the energy of each photon in a monochromatic light of frequency 5 into 10 raised to 14 hertz? So you can clearly see here. So here they are asking us to find out energy. And what else is given here? So here in this particular question, they are asking us to find out energy and frequency is given. So we'll write what is given. So energy, they are asking us to find out. Frequency is given, that is 5 into 10 raised to 14 hertz. H is a value of Planck constant that will be given to you, which is nothing but 6.63 into 10 raised to minus 34 joule into second. So we'll be using formula E is equal to H into nu, and now we'll substitute that values. So E is equal to 6.63 into 10 raised to minus 34 into 5 into 10 raised to 14. And after multiplication, so after multiplication, we'll be getting answer 3.315 into 10 raised to minus 19 joule. And but this answer is in joule. And if we want energy in terms of electron volt, we need to divide to that 3.315 into 10 raised to minus 19 joule to 1.6 into 10 raised to minus 19. So after dividing, we'll be getting answer in terms of electron volt. So let's solve this by log now. So log of 3.315 is 0.5206 and a log of 1.6 is 0.2014. After subtracting, we'll get 0.3192 and anti-log of this number will be 2.085. So this will be our required answer in electron volt. So this is one method. Another method is 3.315 upon 1.6. Here we'll cancel out 10 raised to minus 19 as it is in numerator as well as denominator. So remaining term is 3.315 upon 1.6. So we'll just find out reciprocal of 1.6 by using reciprocal table, and reciprocal of 1.6 is 0.6250. So that will be directly multiplying with 3.315. So again, which will get answer around 2.0. So any one method you can follow to get final answer. Now let's move to next question, which is question number 8. So observation from an experiment on photoelectric effect for the stopping potential by varying the incident frequency were plotted. The slope of the linear curve was found to be approximately 4.1 into 10 raised to minus 15 whole second. Given that the charge of an electron is 1.6 into 10 raised to minus 19 coulomb, find the value of Planck constant. So here it is mentioned that stopping potential by varying the incident frequency. So you can see here stopping potential and frequency. Its slope is given, which is 4.1 into 10 raised to minus 15. So let's write what is given here, whatever is given. So given its slope, which is 4.1 into 10 raised to minus 15 whole second, and is 1.6 into 10 raised to minus 19 coulomb, which is nothing but charge. And they are asking us to find out Planck constant. So value of Planck constant is not given, and H is only we are going to find out. And we are aware of that condition that V naught into E is equal to kinetic energy max. So whatever formula we have studied for kinetic energy max, that we can apply for this and we can get our answer. So V naught E is equal to H nu minus H nu naught. This formula I can apply here. I'll just rearrange that formula. So V naught is equal to H upon E minus H upon E nu naught. I can relate that formula with this standard equation of straight line, that is y is equal to mx plus c. As you can see here, H is Planck constant, E is charge on electron, and threshold frequency. It will be constant for that given metal. So H upon E into mu naught is a constant, and nu is threshold frequency. So H upon E is nothing but that value of slope. So I can write H upon E is equal to, which is nothing but slope, and that is given, which is 4.1 into 10 raised to minus 15. Then our task is to find out H. So I'll multiply E minus 15 into value of E is but 1.6 into 10 raised to minus 19. So again, this is simple multiplication which you can do directly. So we'll get answer 6.56 into 10 raised to minus 34, and this is Planck constant. So unit which will write, that is joule into second. So this is our final answer. H is equal to 6.56 into 10 raised to minus 34 joule second. Now let's move to next question, which is question number 9. The threshold wavelength of a tungsten is 2.76 into 10 raised to minus 5 centimeter. A. Explain why no photoelectrons are emitted when the wavelength is more than 2.16 into 10 raised to minus 5 centimeter. And question B sub question is also given. So let's first find out A, and then we'll find out for B. So in A it is mentioned, explain why no photoelectrons are emitted when the wavelength is more than 2.76 into 10 raised to minus 5. So first let's write whatever is given. So it is mentioned threshold wavelength. Wavelength is given. Threshold frequency is not given, and for wavelength formula symbol is lambda, and as here it is mentioned threshold wavelength, so we'll indicate with lambda naught. So lambda naught is equal to 2.76 into 10 raised to minus 5 centimeter. We can convert this into meter by multiplying it with 10 raised to minus 2 into 10 raised to, so it will become 10 raised to minus 7 meter. So this is threshold wavelength. And here what is given? When the wavelength is more than 2.76 into 10 raised to minus 5. So here it is given wavelength is more than 2, but 2.76 into 10 raised to minus 5 is threshold wavelength. So I can write given is wavelength is more than threshold wavelength. Now let's solve for this. As we are aware that when frequency is more than threshold frequency, then photo emission is possible. Then photocurrent will flow. So, and relation between frequency and wavelength is inversely proportional. So, what will be the condition for photo emission? So, if given wavelength is less than threshold wavelength, then photocurrent will flow or photo emission will be possible. But here you can clearly see given what is given here, wavelength is more than, but in given it is mentioned wavelength is more than threshold wavelength. So exactly reverse condition of this is mentioned. So definitely we can conclude that there will be no photoelectron are emitted. No photoelectrons are emitted. Okay, so no emission of photoelectron because condition is exactly reverse. Now let's solve sub question B. What will be the maximum kinetic energy of electron ejected in each case, each of the following cases? So in B, two subquestions are there. One is for ultraviolet radiation and another is for tungsten surface. First we'll be solving for tungsten ultraviolet radiation and then we'll be doing for tungsten surface. So let's first write whatever is given here. Here it is mentioned if ultraviolet radiation of wavelength is wavelength lambda, which is 1.8 into 10 raised to minus 5 centimeter. So here we are aware of this threshold wavelength and wavelength, and we will try to find out maximum kinetic energy. So first we'll write whatever is given and then we'll substitute. So wavelength, threshold wavelength is 2.676 into 10 raised to minus 5 centimeter, which we have converted into meter, which is 2.76 into 10 raised to minus 7, and given wavelength is 1.8 into 10 raised to minus 5, so which is 1.8 into 10 raised to minus 7 meter. Kinetic energy we'll try to find out. Then value of h is Planck constant and c is speed of light, which is 3 into 10 raised to 8. Then we'll use formula kinetic energy is equal to h nu upon h nu naught, but here wavelength is given. So instead of frequency, we'll use formula in terms of wavelength. So hc into 1 upon lambda minus 1 upon lambda naught. Now we'll just substitute all values and we'll try to get answer. 6.63 into 10 raised to minus 34 into 3 into 10 raised to 8 value of C into 1 upon lambda. So 1 upon 1.8 into 10 raised to minus 7. 10 raised to minus 7 if you will write up, it will become 10 raised to 7 upon 1.8 minus 10 raised to 7 upon 2.76. Then we'll this 10 raised to 7 we'll write outside and 1 up for 1 upon 1.8 and 1 upon 2.76 we will use reciprocal table and we'll just find out reciprocal of 1.8 and 2.76. So let's do it. So reciprocal of 1.8 is 0.5556 and a reciprocal of 2.76 is 0.3623. Then subtraction you need to do. So after subtracting you will get 0.1933 and here multiplication of 6.63 into 10 raised into 3 is 19.89. Now here simple multiplication is there. So 19.89 into 0.1933, and after multiplication you will get 3.844 into 10 raised to minus 19 joule. So this is kinetic energy we have got, but this energy is in terms of joule. So we can convert this energy in terms of electron volt. Now again, if you want to convert joule to electron volt, we need to divide it with 1.6 into 10 raised to minus 19 10 raised to minus 19, 10 raised to minus 19 will cancel out. Again, you can find out reciprocal of 1.6, which is 0.6250. So 3.844 into reciprocal of 1.6 is 0.6250. So again simple multiplication, and which will give you final answer 2.40, and this answer will be electron volt. So this is the required final answer for this first part. Now we'll try to find out for second part. So here it is mentioned radiation of frequency 4 into 10 raised to 15 hertz is made incident on the tungsten surface. So here frequency is given, and here threshold wavelength is given, and we need to find out maximum kinetic energy. So let's try to find out that answer. First we'll write whatever is given, and then we'll substitute in formula. So we are trying to find out kinetic energy now. So formula which we are aware, that is kinetic energy h nu minus h nu naught, but frequency is given and threshold wavelength is given. So h nu minus h, instead of nu naught we'll write c upon lambda naught, because lambda naught is given, and here threshold frequency is not given, that is why we'll write c upon lambda naught only. Now we'll substitute values. H is Planck constant, it will be given to you, and C is 3 into 10 raised to 8. So let's substitute whatever values which we are having. So value of H is common term, so which will write outside. So 6.63 into 10 raised to minus 34 into value of frequency 4 into 10 raised to 15 minus 3 into value of C, 3 into 10 raised to 8 upon 2.76 into 10 raised to minus 7. This 10 raised to minus 7, when it will go up, it will become 10 raised to 15. And both 10 raised to 15, again we can take it out. So remaining bracketed term will be 4 minus 3 upon 2.76. And then we will cross multiply. So 4 into 2.76 minus 3 upon 2.76, and 1 upon 2.76 which I can write outside, and for 1 upon 2.76 I can use reciprocal table. Then reciprocal of 2.76, that is 0.3623, and 4 into 2.76 is 11.04 minus 3. So 6.63, and here 10 raised to minus 34 into 10 raised to plus 15. So remaining term is here, that is 10 raised to minus 19. Then 11.04 minus 3. So it will come 8.04. So again simple multiplication, 6.63 into 0.3623 into 8.04. Straightforward multiplication is there, which will give you 19.31 joule. Now this answer is in joule. Again you can convert here into 10 raised to minus 19 is also there. As this answer is in joule, and if you want to convert this answer in terms of electron volt, again you need to divide it with 1.6. So directly you can multiply with reciprocal of 1.6, and which will give you 12.07. 12.07 electron volt. So dividing this whole term with 1.6, we'll get final answer in electron volt. Now let's move to next question, which is question number 10. Photocurrent recorded in the microammeter in an experimental setup of photoelectric effect vanishes when the retarding potential is more than 0.8 volt. If the wavelength of incident radiation is 4950 angstrom, if the source of incident radiation is changed, the stopping potential turn out to be 1.2 volt. Find the work function of the cathode material and wavelength of the second source. So two conditions are given. In first case, stopping potential is 0.8 volt, and in second case it is 1.2 volt. In first case, when stopping potential is 0.8, that time wavelength is given, that is 4950 angstrom. H and C are constant values. So we'll try to find out work function and the second wavelength. So we'll use formula, again same, kinetic energy max is equal to stopping potential. So whatever formulas are there for kinetic energy max, that we can use, V naught E is equal to. So V naught E is equal to H nu minus work function, and we'll rearrange. So phi is equal to, instead of frequency, Hc upon lambda minus V naught E, and then we'll substitute values and we'll try to find out work function, that is phi. So phi is equal to question mark and lambda dash. Lambda dash means in second case whatever will be the wavelength, that is lambda dash. So that we'll try to get. So let's substitute all values and try to get answer. So 6.63 into 10 raised to minus 34 value of h, 3 into 10 raised to 8 value of c upon lambda is 4.95 into 10 raised to minus 7 minus 0.8 into 1.6 into 10 raised to minus 19. Now here you can see this 10 raised to minus 34 and 10 raised to 8 and 10 raised to minus 7, when it will become it will go up, it will become 10 raised to plus 7. So when we'll do this part, so we'll get answer 10 raised to minus 19 and 6.63 into 3. So that multiplication is 19.89 upon 4.95 minus 0.8 into 1.6 is 1.28 into 10 raised to minus 19. This 10 raised to minus 19, we can take it out. So remaining term is this 19.89 upon 4.95, that we can find out separately by log. So log of 19.89 minus log of 4.95. So let's do it separately and substitute final answer here. So it will become easy for you. Another way is find out reciprocal of 4.95, multiply it with 19.29. That way also you can do. So answer for 19.89 upon 4.95 after finding log, antilog and subtraction, 4.019 minus 1.28, common term is 10 raised to minus 19. So after subtracting 2.7838 into 10 raised to minus 19. But this answer is in joule. You can convert it into electron volt by multiplying it with reciprocal of 1.6. So final answer 1.711 electron volt. So this is value of work function. Now we'll try to find out lambda dash, second wavelength. So V naught E is equal to Hc upon lambda dash minus work function. We are trying to find out wavelength. While rearrange this formula, V naught E plus phi is equal to Hc upon lambda dash, as we need to find out lambda dash. So let's rearrange this formula such a way that lambda will get in terms of lambda dash is equal to. So I'll arrange. So this will be formula lambda dash is equal to hc upon v naught e plus 5. And now we'll substitute all values. Here this should be v naught dash, which is 1.2. H is Planck constant, C is 3 into 10 raised to 8, E is 1.6 into 10 raised to minus 19, and work function, which we have already done, that we will substitute. So 6.63 into 10 into 3 is nothing but 19.89, and 10 raised to minus 34 and 10 raised to 8. That is nothing but when we will do that part, we will get 10 raised to minus 26, and in the denominator 10 raised to minus 19, it's common term which will take it out. So then in 1.2 into 1.6, that you will have to multiply separately, and then you will have to add 2.738. So after doing that part, you will get 4.658. In numerator it is 10 raised to minus 26, and denominator 10 raised to minus 19 is there. Then again two ways are there. Log of 19.89 minus log of 4.658, that way also you can do. Otherwise you need to find out reciprocal of 4.658, and that reciprocal you need to multiply it with 19.89. So I'll write that log antilog part. So when you will solve 19.89 upon 4.658, after doing log, anti-log of 19.89 is 1.2987, log of 4.658 is 0.6682, then anti-log, then you will get 4.271. So our final answer is 4.271 into 10 raised to minus 7 meter. So this will be our final answer in meter. And if you want to convert it into angstrom, then you will be writing 4271 angstrom unit. You convert it into 10 raised to minus 10 format. So this will be answer for question number 10 for second wavelength. Thank you.